This video details the simulation of Bose-Einstein condensate breathing modes. Our primary focus is the numerical integration of the Pitaevskii equation using the split-step Fourier method and trap-quench dynamics. The core problem involves simulating the breathing mode of a two-dimensional Bose-Einstein condensate. This is achieved by suddenly changing the harmonic trap and observing the resulting time evolution. The Pitaevskii equation is our physics engine. It includes a kinetic term for wave dispersion, a harmonic potential term for confinement, and a nonlinear interaction term representing atomic interactions. The breathing mode is initiated by a sudden trap quench. We move from a tight initial confinement with an initial frequency of 1.0 to an instantaneous relaxation to a final frequency of 0.7 at time t equals 0. This sudden reduction in the confining potential energy causes an energy imbalance. The initially compressed ground state expands and contracts iteratively, driving the observable breathing mode. To perform the numerical integration, we discretize the spatial domain. We use a 256 by 256 grid of points, covering the spatial boundaries from -10 to 10 in both dimensions. The split-step Fourier method efficiently integrates the Pitaevskii equation. It iteratively applies the potential and nonlinear phase in real space and the kinetic propagator in momentum space, using fast Fourier transforms to switch between the two. The simulation uses specific parameters. Physical constants are set, trap frequencies are defined, and we integrate over a time maximum of 20.0 with a time step of 0.01. The spatial grid is 256 by 256. Initialization begins at t equals 0 with the normalized ground state. This state is calculated within the initial tight confinement before the trap-quench dynamics are introduced. Our first lens tracks the macroscopic density evolution over time. These raw density maps visualize the bulk expansion and contraction of the quantum gas, setting the baseline for analysis. The second lens maps localized density shifts using a diagnostic that calculates the change from the initial density. Positive regions in red indicate outward mass flow, and negative regions in blue show where density has been vacated. The third lens uses scalar signatures of the breathing cycle. We observe an out-of-phase oscillation between the root mean square radius and the peak density, providing the mathematical signature of the breathing mode. The split-step Fourier method provides a stable engine for integrating nonlinear quantum dynamics. The trap quench successfully bridges theory and observable macroscopic quantum phenomena, confirming the predictable, rhythmic energy exchange. This video demonstrates simulating quantum breathing modes using a split-step Fourier approach to Bose-Einstein condensate dynamics. The catalyst for the breathing mode is the trap quench, where the initial ground state is instantly out of equilibrium with the new Hamiltonian. This triggers the oscillating expansion and contraction, beginning the breathing mode. The simulation pipeline starts with preparing the ground state. Next, we quench the trap potential and evolve the system using the split-step FFT method. Finally, we save snapshots and track diagnostics to interpret the dynamics. We define the physical constants for the simulation, with h-bar and mass m set to 1 and the scattering length a_s at 0.005. The interaction strength g is a small positive value, confirming weak atomic interaction. Step 1 involves discretization and initialization. We use a 256 by 256 grid over the spatial range of -10 to 10 in x and y. The initial state is normalized to ensure the probability integral equals 1. Initializing the condensate ground state uses a specific mathematical expression for the wave function psi0, which is then explicitly normalized. The setup is copied into a complex array to accommodate time evolution phases. Step 2 builds the quenched harmonic potential. Since the final frequency is less than the initial frequency, the trap is effectively wider. The cloud is now too confined and immediately begins to expand, initiating the breathing mode. This video will explore the Fourier space kinetic propagator, focusing on how to efficiently evaluate the Pitaevskii kinetic energy step, from theory to Python implementation. The governing physics is described by the Pitaevskii equation. The kinetic operator term, highlighted in red, is central to our discussion. We are isolating the kinetic part of the Hamiltonian, which includes the Laplacian operator. In 2D, the Laplacian expands as the sum of second partial derivatives with respect to x and y. Evaluating the Laplacian in real space is computationally expensive. It requires heavy numerical second derivatives at every grid point, repeated at every time step. The Fourier paradigm shift transforms calculus into algebra. The heavy derivatives in real space are replaced by simple multiplication in Fourier space, using the Fourier transform. Applying the derivative transformation again for the second derivative introduces a crucial minus sign, since I squared equals -1. Similar results are found for the y direction. The full Laplacian in Fourier space collapses into a simple scalar, negative k squared. This minus sign is essential. Replacing the Laplacian with the new Fourier scalar in the kinetic operator yields a simplified form. In Fourier space, the kinetic operator becomes simple multiplication. We define the kinetic time evolution propagator by isolating the kinetic part of the general time evolution operator. Substituting the Fourier space form of the kinetic operator gives this exponential expression. Canceling one factor of h bar simplifies the formula, resulting in the final mathematical formula for the kinetic propagator. This is the three-step numerical recipe. First, the fast Fourier transform, then multiplication by the kinetic propagator, and finally, the inverse FFT back to real space. This loop repeats for each time step. The mathematical formula translates directly into Python code, defining k squared and the exponential kinetic propagator, EXPK, for efficient computation. This cheat sheet summarizes the problem of heavy derivatives in real space, the Fourier transformation where calculus becomes algebra, the resulting kinetic propagator, and the three-step numerical loop. This video explores evolving the gross Pitaevskii wave function using the split-step Fourier algorithm with renormalization. This highly accurate, stable numerical method allows us to evolve the wave function forward by one time step, delta t. The core equation splits into the kinetic energy operator, t hat, and the real space part, u hat. The conflict is that t hat and u hat do not commute, meaning we cannot simply separate their time evolution exponents exactly to solve the equation. The symmetric Strang splitting is a technique that decouples the operators. By splitting the evolution into a symmetric sequence, we achieve second-order accuracy in time, approximating the evolution into half real space, full Fourier space, and half real space steps. Let's explore the Strang splitting in detail, providing a step-by-step visual proof of second-order accuracy. We will strategically simplify the algebra to avoid, quote, operator algebra fog, and show exactly why this approximation holds. The core problem, or mischief in quantum simulation, arises because the kinetic operator hat and the potential operator v hat usually do not commute. This non-commutation means that EA plus B is not equal to EAEB, which is what we need to solve. To simplify the algebra, we define simpler symbols, x and y, proportional to the time step delta t. Our task is to prove why the exact exponential is approximated by the symmetric Strang splitting formula. First, we establish our exact reference result. Expanding the exponential ex plus y, using the ordinary exponential series up to second order in delta t, we must keep x, y, and yx separate, because the operators do not commute. Next, we expand the split factors of the Strang product ex/2, ex/2 independently, keeping terms up to the second order in delta t squared. We begin by multiplying the first two factors, a and b, distributing term by term. We systematically drop terms that exceed the second order, which scale as delta t cubed or higher. Consolidating the intermediate state, we gather all surviving terms up to the second order. Notably, the non-commuting term xy/2 has emerged naturally from the distribution. Now we distribute the final factor ex/2. We substitute the expression for ab and multiply by the expansion of the last factor. This is broken down into multiplying by the identity I and by x/2. The final part of the multiplication involves terms from multiplying ab by x squared over 8. We discard all resulting terms that scale as delta t cubed or higher, keeping only the I times x squared over 8 term. Adding all valid contributions together from steps 6a, 6b, and 6c, we sum the constant, first order, and second order terms. We simplify the coefficient for the x squared term to 1/2. The exact exponential and the split product match perfectly up to the second order in delta t. This confirms the second order accuracy of the Strang splitting formula, proving that the error scales as delta t cubed. Restoring the original quantum operators t hat and v hat, we substitute back the definitions of x and y. This result is exactly the Strang splitting formula, ready for deployment in quantum simulation. The exact formula equals the split formula plus an error term of order delta t cubed. However, over many time steps, these local errors compound. The total accumulated global error becomes of order delta t squared, establishing strang splitting as a second-order accurate method. This video describes the 6-step continuous data pipeline for propagating the Pitaevskii wave function. One complete time step moves the wave function continuously back and forth between real space and k-space. Step 1 is the first half step in real space. This involves updating the wave function Psi-n using the nonlinear mean field potential to obtain Psi-1. Step 2 is transforming the wave function to Fourier space using the fast Fourier transform. This is necessary because real space cannot efficiently handle the kinetic operator. The output is Psi-1 in k-space. Step 3 is the full kinetic step in Fourier space. The kinetic update occurs over one full time step delta t, utilizing the pre-computed kinetic propagator, express k. The resulting wave function is Psi-2. Step 4 transforms the wave function back to real space using the inverse Fourier transform. This brings the wave function back for the final spatial step. The output is Si2. Step 5 is the second half step in real space. This closes the symmetric split. It is crucial to compute the spatial update using the newly updated density, Psi2, not the old density, resulting in Psi3. Step 6 is renormalization, which corrects for floating point drift. This process calculates the numerical norm and rescales the wave function to the target norm n0, yielding the final output, Psi-n plus 1. This slide shows the complete Python implementation of the 6-step data pipeline, which can be summarized into 4 key code steps. The split-step Fourier algorithm provides a robust and efficient foundation for Pitaevskii evolution by combining symmetric splitting, FFT efficiency, and stable renormalization for particle conservation. Small time increments are necessary for numerical stability and accurately resolving the rapid oscillatory motion of the breathing mode. In our simulation, we use a time step of 0.01 over a total time of 20.0, resulting in 2,000 iterations. The split-step FFT algorithm uses a symmetric split, alternating between half-step updates in real space and a full-step update in momentum space. This significantly reduces time-stepping error. Renormalization is applied after each full step to correct finite precision drift. We capture the motion using 2 types of diagnostics. Snapshot storage saves the absolute density and density change periodically. Scalar diagnostics, tracked at every time step, include the RMS radius for expansion/contraction and the inversely related peak density. The dynamic involves an inverse relationship. As the mean square radius, RRMS, increases, the peak density decreases. RRMS is calculated from the spatial coordinates weighted by the current density, and peak density is the maximum density value on the grid. Density change maps, delta n, isolate movement by comparing the current density to the starting density. A fixed, symmetric color scale ensures comparability between snapshots. Red indicates density increased, and blue indicates density decreased relative to the initial state. Visualizing the absolute density shows the macroscopic cloud size throughout the simulation, while density change maps highlight subtle mass transfer. Absolute density plots allow for direct observation of the condensate's expansion and contraction over time. Tracking the RRMS radius provides the direct scalar signature of the breathing motion. The regular oscillations show the cloud expanding to its maximum radius and compressing inward by the trap over the course of the simulation time. Tracking the peak density confirms mass conservation. As the cloud expands and the RMS radius increases, the peak density drops, and vice versa. The peak density curve perfectly mirrors the RMS radius during the breathing cycle. The final condensate state shows a clear mass concentration at the center, with density decreasing outward. Using a common scale for all density plots is essential for accurately comparing the physical size of the cloud over time. Density change maps, delta n, visualize the dynamics. The symmetric color scale makes subtle departures from the initial equilibrium state immediately obvious. Red areas indicate where density increased, and blue areas show where density decreased relative to the start. The trap quench, a sudden environmental shift, forces the matter to redistribute. By seamlessly toggling between real and momentum space to solve the gross Pitaevskii equation, we accurately capture the resulting periodic quantum breathing motion shown in the RMS curve. The RMS radius versus time plot is the cleanest observable for the breathing mode. The rhythmic rising and falling perfectly captures the outward-inward motion. The cycle repeats indefinitely. The cloud pushes out, is pulled in, overshoots, and repeats. The simulation involves 5 steps: prepare the ground state, quench the trap, evolve using the split-step FFT, observe by saving density and change arrays, and interpret by extracting RRMS to prove the breathing dynamics.